Okay, is that better? Thank you. All right, good morning. We're together now. You can hear me. Okay, so we're going to get started with where we left off last time. We were talking about Newton's laws, Freebody diagrams, F equals ma, and that's where we're going to pick it up today. All right, so we've got this activity here. We've got the water skier being pulled by a boat, and they're being pulled at constant speed. Because the weight of the skiers and the type of skis they're using varies, they experience different resistive forces from the water. Values for this resistive force is given in the problem. So rank these based on the net force on each of these skiers. It says the water skiers are pulled at constant speed by a tow rope attached to a boat. Because the skiers have different weights and skis, the resistive force between them and the water varies. The value of the resistive force is given. What's the net force on each of these skiers? So if they're being pulled at constant speed, there we go. If they're being pulled at constant speed, the acceleration is 0. So the net force has to be 0. Zero for all. Okay? Now, find the tension in the rope. Let's draw a Freebody diagram for the person. Draw a Freebody diagram for the skier. So what's touching the skier? The water is touching the skier, the ground, the water. That's interacting two ways, right? Through a normal force and through a resistive force. They're calling it RF. Drag, right? Drag with the water. kind of like friction, but we'll call it RF, resistive force. What else is touching the skier? The rope. So there's tension in a rope. That's everything that's touching the skier. What can reach in from a distance? Gravity. So the tension in rope A has to be equal to the resistive force, right? These two forces right here have to be equal if they're going to cancel out to zero and you're going to get no net force, right? So in each case, if we wanted to find the tension in the rope, it would be equal to the resistive force. So B would be 800. C would be 900. And the last one would be 750. Okay, now let's make it more interesting, okay? We'll have our skier will be 50 kilograms, and they'll be accelerating this time. The acceleration is going to be 2 meters per second squared to the right. All right, find the tension in each rope. So what are we going to say? We're going to say the sum of the forces has to be equal to MA. And so the net force is in the, so we can split this up. This is a vector equation, right? We can split this up into X and Y. If we call this our X direction and this our Y direction, we can split this up. Sum of the forces in the X direction has to equal M times the acceleration in that direction. And the sum of the forces in the Y direction has to be M times the acceleration in the Y direction. And we pick a positive direction. I'll pick to the right and up as my positive directions. Now, what's the acceleration in the Y direction? The vertical direction. 0, right? The skier is not coming up off the water, not going down into the water. The skier is always at the same Y position. There's no movement at all in the Y direction. Acceleration in the Y direction is 0. So this tells us the sum of the forces in the Y direction are what I'm calling the vertical direction has to be 0. What does that mean? That means the normal force has to equal the force of gravity. That's what that tells us. Okay, we already knew that though, right? Let's look at the other direction. So T is in my positive direction. I'm looking at this direction now, right? Sum of the forces in the horizontal direction. So T, the tension in the rope, is pointing in the positive direction. My resistive force is in the negative direction, so I'm going to put minus there. And that has to equal M times the acceleration. And that those numbers were given. So T minus RF has to equal 50 times 2. So the difference between them has to be 100 newtons, right? So the tension is equal to the resistive force plus 100 newtons. So in each case, we just add 100 newtons. So in A, it becomes 850, right? And for B, 900, is that right? And C, 1,000. And D, 850. Okay. You didn't think I was done, did you? We'll leave M 50 kilograms, but we're going to change our acceleration 2 meters per second squared to the left. Find the tension in each rope. So it's the same approach as last time. We say sum of the forces has to equal MA. To the right is my positive direction. So I have tension minus resistive force is MA. M is 50. And what is A this time? It's 2, but it's in the negative direction. Don't forget that negative sign. So the tension is equal to the resistive force minus 100. So you can fill them all in. Okay. All right. Let's talk about friction. So we've been talking about friction a little bit, but we need to talk about it a little bit more. And there's some formulas that help us actually calculate the friction in some situations. So let's talk about friction. So here I've got a block sitting on a surface. And I'm going to apply some kind of a force to it. Now, if I plot the friction force, I'm going to run out of room here. Okay, so if my box is just sitting there on the surface and I'm not touching it, What's the friction force? 0, right? Now I'm going to pull with a 1 Newton force. My box just sits there at rest. What's the friction force? 1 Newton, right? Now I'm going to pull with a 2 Newton force, right? The box just sits there at rest. What's the friction force? 2 Newtons, right? We got that. As I pull harder and harder and harder, the friction force gets bigger and bigger and bigger, and it looks something like this, right? There we go. Okay, it keeps increasing. As I pull, the friction force gets bigger and bigger and bigger. Then what happens? I pull a little bit harder, and that box now breaks free and starts sliding along the surface. And when that happens, this does something like this. So this region here is what we call static. Because there's no motion between the block and the table, right? There's no motion. Those two surfaces are stationary with respect to one another. And this region out here we call kinetic, because there's motion between them. The box is sliding across the table. So if you look at the two surfaces, they're moving with respect to one another. There's sliding there. Kinetic friction. Okay, so this, we're going to call this static friction maximum, right? Static friction changes, right? It can be 0 and it can increase, but it has some maximum value that it can't go beyond, right? And so that number we can calculate. You can't calculate static friction by itself without knowing some other information, right? Static friction might be 0. It might be 1. It might be 2 newtons. It might be 1.65 newtons. We don't know what it is unless we look at the other forces and analyze the situation. Then we can figure out what the static friction is. But we can calculate the maximum it can be. We can calculate the maximum static friction force from this equation. So it's always less than or equal to some constant times the normal force. Or another way of writing that, the maximum is equal to that constant times the normal force, however you like to think of it. So what does the friction force depend on? You might think that the friction force depends on the surface area, the contact area with the surfaces. You might think it depends on the weight of the object. You might think it depends on other things. But what happens is, as you change the surface area, let's say I have a book like this. If I put this book on the table like this, there's lots of contact area here with the table. But each little section, each little square centimeter of surface doesn't have very much book weight pushing down on it, right? Whereas if I tilt my book up and I stand it on my surface this way, there's not very much contact area with the surface, but each little square centimeter has a big amount of weight pushing down on it. It turns out that all that really matters is the normal force, right? The normal force tells us the interaction between the table and that object, right? That's what the normal force tells us. It's the interaction between those two objects. How hard are they pressed into one another? So the normal force makes perfect sense. Surface roughness is what this coefficient is all about. So the normal force tells us how hard are these two objects being pressed together, and this coefficient mu, that's the Greek letter mu. It's a little hard to tell sometimes from my handwriting, but that's the Greek letter mu. That mu depends on the surfaces. Some surfaces are very slippery. They have a small coefficient of friction. Some are rough and hard, rough and hard to slide across, and they have a high coefficient of friction. So that coefficient of friction depends on the surfaces. The normal force tells us how hard they're being pressed together. Now, our kinetic friction is much simpler. It never changes. It doesn't matter if the block is sliding at 1 meter per second or 100 meters per second. Coefficient of kinetic friction is always the same. See how this line here is just a horizontal line. Well, maybe I should draw it more like a horizontal line, but it comes down and then it's just a horizontal line there. Okay. There. Constant, never changes, flat, constant line. So if we draw this one back to our axis, we could call that F kinetic friction force. And that's equal to some coefficient, mu, times the normal force. But the coefficient is different. You can see that it's going to be a little smaller, right? Looking at the graph, the way I drew it here. The force, the static friction force increases, and as soon as it breaks free from the surface, the friction force drops a little bit. The kinetic friction force is less than the maximum static friction force. So that's how I drew it here. So mu sub s is larger than mu sub k. Good question about this change here. I drew it, I would say it's instantaneous. I think it's more instantaneous. This happens in a very short time interval. This right here. I kind of drew it like a curve, but I could have had it come. I mean, there's got to be some time interval, right? How's that? Is that better? I think your book draws it slightly curved. This is fine. I view it as happening in an instant, instantaneously. So what happens is it's just a manifestation of how the friction force works. Remember our picture of the rough surfaces pressing into each other, right? So so once you press, you have a jagged surface and another jagged surface. Oops. Anyway, you get the idea. And right here, you have two surfaces that are kind of pressed together. Well, you can press them pretty hard, right? And then all of a sudden they slip and they're just gliding across the tops. And so you don't get as much resistance when you're sliding that block across the surface and there's motion, then at that maximum point when they're actually pressed against each other and the normal force between the two surfaces is reacting and you get a bigger force there. Yes, it takes more force to make the block start moving than it does to keep it moving. Yes. Okay, so we have our cars these days, almost all of them have anti-lock braking systems, right? ABS, anti-lock braking systems. What is that all about? When the wheel on your car is rotating, you are in what kind of friction mode? You are in static friction mode. Because if the wheel is free to rotate, think about what's happening between the rubber and the road. If the wheel is rotating, there's no motion between the rubber tire and the road. That's static friction, okay? If the wheel locks and doesn't rotate anymore, then what happens? Your car goes into what's called a skid, right? Your car the rubber is sliding across the road, right? You're in kinetic friction then. You don't want your wheel to lock. You know, when you hit your brake really hard, those wheels lock and then they don't turn anymore and you're in a skid. When you're in a skid, you can't steer. Your car is going to go whatever direction it was going before you went into the skid. You have no control anymore. But if you can, and you're in kinetic friction mode, which means that you're at a slightly lower friction than the maximum static friction force, right? So if you can keep your wheel rotating, in the old days, they used to tell us to pump the brake. Don't just slam your foot on the brake. You let up and then you hit it again, you let up, you pump the brake, because then every time you press down and it tries to lock the wheel, you ease up a little bit. Now they have a computer that does it for you, right? That's the anti-lock braking system. It's a computer. You slam your foot on the brake and the computer pumps the brake and controls it so that every time the computer senses the wheel stops rotating, it releases the brake pad slightly so it starts to rotate again. Then it squeezes some more. So the computer takes care of that for you. The biggest benefit is you can still steer your car. If your wheels are rotating, you can still steer your car. The side benefit is that it's possible your car could stop in a shorter distance. It depends on if you're really at the maximum static friction force the whole time or not. I'm not sure you really are, but it's possible you could stop your car in a shorter distance. The main benefit is you retain steering control. Okay, we go okay with this one now? And coefficients of friction. For our cases, they're always less than 1 for our cases. So, you know, 0.2, 0.3, 0.4, those are very typical numbers that we see for the problems that we're working. Sometimes people ask me about race car tires. And race car tires, so one of the things you'll see here in our equation, we just talked about the fact that this does not depend on surface area, right? It does not depend on surface area, just the normal force. Well, race car tires, there is a benefit to having a larger contact area. Sometimes students ask me, well, why do they make race car tires big? There's supposed to be a bigger contact area. There's 2 benefits to that. The first one is that the tire is going to heat up, right? As it's rubbing on the road, and you've got that friction, and it's trying to push the car forward, the tire heats up. So even if you make the tire bigger, even if you don't get any more friction force out of it, you're spreading the heat over a larger area, and your tire might last a little bit longer. The other thing is that race car tires don't follow this equation. Race car tires are actually sticky. If you touch them, they're sticky. They have a coefficient of friction greater than 1. So for our purposes, we're not going to take into account like if something has glue on it or stickiness, right? We just want 2 smooth surfaces, what's the coefficient of friction when they slide together, it's going to be less than 1. But if you have surfaces that can deform and surfaces that are sticky, and there's actually like a chemical bond trying to grab onto the road, well, that's different, right? That has a coefficient greater than 1. In fact, I think they're greater than 3. Big coefficient of friction. And so in those cases, having a larger contact area is beneficial. So we're dealing with simple cases, just rigid surfaces sliding across each other, or static friction, either way. But rigid surfaces, not sticky, stuff like that. So we're dealing with a simple case of friction, but it's for most cases it's applicable. There's nothing special about 1, I don't think, for coefficients of friction. All right, so now we have the tools. We've been talking about friction. Now we have the tool to actually use it and incorporate friction into our equations. Okay, so now we want to talk about inclined planes. We're starting to put some things together, make our problems a little more real world, right? We've been ignoring friction for a while. Now we have the ability to deal with friction. Now we're going to have the ability to deal with surfaces that aren't flat, surfaces that are at an incline. Okay, let's draw our free body diagram. Excuse me. Are you drawing a free body diagram? Take a stab at the free body diagram for this box at rest, sitting on an incline. If this is my box and this is my incline, then what's touching my box? The surface. The surface can interact 2 ways, right? Through a normal force that's perpendicular or normal to the surface. So that would be this one here. Normal to the surface would be that way, right? And through a friction force parallel to the surface. And what direction would my friction force be? Up the incline, right? Because if the friction force wasn't there, this box would be sliding down the incline. So up the incline, we have friction. And what kind of friction is it? Static friction. The object is not moving, right? It's sitting there at rest. So that's everything that's touching. That's everything that's touching the block. I'm going to make that just a little bit shorter. And what can reach in from a distance? Gravity can reach in from a distance, right? Gravity points toward the center of the earth, right? Straight towards the center of the earth. So that's my free body diagram. Did anybody have this as their free body diagram? Nobody had this one. Come on. Is this okay? Anything wrong with that? You buy that? We all agree gravity is doing this, right? Gravity is pulling towards the center of the earth, right? And our object is not moving. So the surface must be doing that. I think that's okay. But what we typically do, we don't typically treat the normal force and the friction force combined into one force called F surface, right? That's not usually the way we think of it. We break this force up and we say that surface force is really a normal force plus a friction force. And when we do the vector addition between the normal force and the friction force, we should get F surface, right? So if we add those two forces together, we could call it F surface. But we like to break that up into the components and think about sort of how those two forces manifest themselves and what causes each one. And it's a little simpler to think about that way. Okay, so what do we do next? We want to do this, right? We want to do Newton's second law. That's what we want to do, right? We want to try to figure some force out here, right? So we want to say the sum of the forces is ma. This is a vector equation, right? And typically, sometimes that we can leave it as a vector. Usually we break it up into components. It's a little easier to deal with. So we'll break this up into our components. So we say the sum of the forces is ma in one direction, and the sum of the forces is ma in the other direction. And we need to pick a coordinate system. So usually what we'll do is we'll think about acceleration. What would this object do if it was moving, right? Where would the acceleration point? Well, the object's probably not going to jump up off the surface, and it's probably not going to fall down into the surface. It's probably always going to be along the surface. And any acceleration that takes place will be along the angle of the surface. So I would make my coordinate system aligned with the angle of the surface, aligned with the acceleration, if there was acceleration. So we could pick this as our coordinate system. And we could call it anything we want. We could call this the X direction and this the Y direction. That's fine. I guess I'll do that here. So we would say the sum of the forces in the X direction has to equal m times the acceleration in that direction. We need to pick what's our positive direction. I'm going to call up the incline my positive direction. And then we'll say the sum of the forces in the Y direction has to equal the mass times the acceleration in the Y direction. And I'm calling that my positive direction. And in this case, the box is at rest. There's not acceleration in any direction, right? So both a sub x and a sub y are 0. So we have sum of the forces in the x direction has to be 0, and sum of the forces in the y direction has to be 0. So now we just have to figure out what our forces are. So let's go back and look at our free body diagram. We see the normal force is already, it's all in the y direction. We can just leave it like that. The friction force is all in the x direction. We can leave it like that. But our force of gravity has components in both directions. So we need to break it up into the components that match our coordinate system so we can add it with the other vectors. So how do we do that? Well, there's a angle here, and it turns out if we know this angle with the incline with respect to the horizontal, then let's take a look at our box. The normal makes a right angle here, right? And this makes a right angle here. So if you follow the logic, this angle is also theta. Work through it a couple of times and convince yourself that that angle is always theta. So the force of gravity, let's take a look at our box one more time here. The box is here. Force of gravity is this one, right? We want to break that up into a component that's normal, the y direction, and a component that's parallel to the surface, the x direction, and we know this angle is theta. So if that angle is theta and the hypotenuse is f sub g, then the y component is f sub g times the cosine of theta, and the x component is f sub g times the sine of theta. And what is the force of gravity? It's just mg, right? So this is mg sine theta, and the other one is mg cosine theta. We okay with that one? That's one of those things you just have to do it a bunch of times and you'll start to catch on and see what's going on. But make sure you understand how it breaks up. Don't mix up your sines and cosines. Okay, so let's come down here now. So we're adding up, we're saying the sum of the forces in the x. So we could draw, I could draw one more free body diagram here in component form. So I've got my object. I'm going to leave my incline at an angle like this. I've got my static friction and my normal force and my force of gravity in the y direction and my force of gravity in the x direction. I guess I should use capital F since that's what I always use. Okay, so that's what my free body diagram looks like after I break up the forces. So I'm taking the x direction. Let me use green for this one. So this is my x direction. So I've got one force that points in the positive x direction. That's the static friction force. And I have one force that points in the negative x direction. That's the force of gravity along the incline. So minus Fg sub x. And those two have to add to be 0. The sum of the forces in that direction has to be 0. And then in the y direction, I'll use red here. The y direction is this one. So in the positive direction, I've got my normal force there, right? Pointing in the positive direction. And in the negative direction, minus, I have Fgy. And those have to add up to be 0. I have no acceleration in that direction. And now I can plug in what I know for these different things. So I know F gravity in the x direction is mg sine theta. And I know In the y direction, it's mg cos theta. So this one tells me, one of them tells me what my normal force is. Normal force is equal to mg cosine theta. So that's why we do the perpendicular direction, right? I called it the y direction here. I don't always call it the y direction. You'll see later. But that's why we do the perpendicular direction to the motion, to figure out what the normal force is. The normal force is not always the weight of the object, right? If you just have an object sitting on a flat surface, then the normal force is just the weight of the object. But that's the very simple case, right? As soon as you tilt that surface, make it an incline, the normal force is not the weight of the object anymore. Or if you put something on top of the object, or if you're pulling at an angle or pushing at an angle, then the normal force is no longer the weight of the object. Why do we do this perpendicular direction? To find the normal force. Why do we need the normal force? Because we have friction in our system. Friction depends on normal force. So this gives us the normal force. Then we plug that in if we knew we were using, if the box was sliding, we could plug that in for kinetic friction. If we knew that the box was just at its maximum static friction point, we could find theta maybe, such that the box, the maximum angle we could get if we were given the static friction force, then we could plug it in. But in this case, I think we're done with this illustration. But you get the idea here. We do the perpendicular direction to find the normal force, and usually we plug that into the parallel direction of the incline to figure out whatever we're looking for. Friction force, tension in a string, acceleration, something like that. Okay. So we're talking about friction. Let's go over some interesting applications. Maybe you've thought about some of these, maybe you haven't. But friction is one of those things that, you know, it's a little odd. Sometimes you want to maximize it, right? If you're running, right? Running, you need to be able to speed up, slow down, make turns. If you're playing basketball, right? You turn quickly, you want maximum friction. Running shoes have soles that maximize friction, like race car tires do, right? Soles that maximize friction. Race car tires have coefficients of friction greater than 3, right? And objects that we deal with in this class, it's always going to be between 0 and 1. So sometimes you want to maximize friction, good grip. Sometimes you want to minimize friction, right? So we use lubricants in engines to reduce wear. Friction causes small parts to break off and they rub together and wear out your engine. So we have oil and things in there. Other places where you have rubbing and you don't want it, we put oil or other lubricants, right, to make it smoother and reduce friction. We want to reduce friction a lot of times. And maybe you saw in chemistry class, one of the things that they've come up with are these buckyballs. 60 carbon atoms arranged in the shape of a soccer ball, and they act like microscopic ball bearings in modern lubricants, buckyballs. Maybe you've seen those in chemistry class. And then in sports, right, trying to go fast, trying to turn, things like that. My kids played roller hockey. Here's a picture of one of my sons fighting off a player from Great Britain in a roller hockey match. And those, they wear these inline skates with these rubber wheels. Those wheels are high tech. You know what that means? I'll translate that for you. It means they're expensive. So you might think at first thought that you would want those wheels to be soft rubber so that you get really good grip and you can turn quickly and make sharp turns. Well, think about this for a second. If those wheels were really soft, so you had really good grip, you wouldn't be able to go very fast, right? It's kind of like running through sand, right? When the surface becomes really, really soft, every time your foot tries to push off it, a lot of that energy just gets dissipated in the surface moving, right? So if you're trying to skate fast and you have soft rubber on the wheels of your skates, it just dissipates a lot of energy. You can't skate very fast. So you want the wheels to be, you don't want a lot of deformation, right? You want them to be pretty rigid, but yet you want them, the surface, to be soft enough and sort of tacky enough that they'll give you friction. So what do? They make an inner core on those wheels that's really rigid. So the wheel doesn't deflect and bend much, but they put a thin coating of a soft rubber around the outside so you get good grip. So high-tech design, but that means that thin layer on the outside wears out pretty quickly. And like I said, those wheels, you know, they're like $12 a piece, and there's 4 wheels on each skate, 8 wheels. It's like $100 every time you have to change your wheels out. Anyway, a lot of interesting applications for friction. Just thought I'd talk about that for a minute before we take our break. So we'll take a break now. We'll come back and we'll link to, now we're going to have 2 objects in our system linked by a pulley. Okay, so take a 10-minute break, and then we'll come back and do more Newton's laws. Okay, so let's do an example where we have a pulley now, and we have a second object in our system, and they're connected by a rope over this pulley. And this time I'll actually tell you what you're trying to solve. Maybe that'll make it a little easier. Okay, so we've got a box on a horizontal surface, got a pulley over here. And another box over here. This is 1 and 2. So given some friction coefficient, the masses, and the fact that that pulley is frictionless, sorry, massless, well, massless and frictionless. We're going to find the tension in the rope and the acceleration. Okay, so massless pulley, what does that mean? That means that it doesn't take any difference in tension between the 2 ropes to cause that pulley to accelerate with the masses as they move. If the pulley had mass, then it takes some, well, let's think of it this way. If I had a box here, and there was a string pulling on this side and a string pulling on this side, and there's no the box is moving, but it's not accelerating, we know T1 equals T2, right, if there's frictionless surface. And if the box is accelerating, we know if it's accelerating in this direction, we know T1 would have to be greater than T2, right? But if the box is massless, then T1 could equal T2 and we could still have acceleration, right? It's like it's not even there, right? I could just have 1 rope here. It's not even there. And I could still have acceleration. So that's the idea with this pulley. If that pulley has mass, the tension in the rope on each side of the pulley has to be different. But because it's massless, then the tension on each side, the massless pulley means that T1 is equal to T2 is equal to T. So if we call this T1 and we call this T2, now we don't have to call them T1 and T2 anymore. We can just call them T. There's only 1 tension in this rope. It's the same everywhere. The pulley can change the direction of it, but it can't change the value if it's massless. Now, When are pulleys going to have mass? In a few weeks, when we have the tools to deal with objects that can rotate, right? Solid objects that can rotate. Then our pulleys will have mass, and T1 will not equal T2. There'll be a different tension on each side of that pulley. But right now, this is the way we'll deal with it. So, we'll, if we were to release this system, what would happen to it? It would start to move, right? If M2 was big enough to overcome the friction, right? So let's just say this system is moving to the right. Block 1 is moving to the right. And because you have to know which way it's moving in order to get the direction of the friction force correct. I don't think it matters which one is more massive. As long as we know it's moving to the right, we can solve this symbolically. So let's do that. So Freebody diagrams for the two blocks. Go ahead and draw those. I'll do the easy one for you. What's touching M2? The rope. What can reach in from a distance? Gravity. And what is that equal to? Force of gravity is just mass times g, right? mg. Okay, let's do 1 now. What's touching it? The surface. That interacts two ways, through a normal force and through a friction force. What direction is the friction force? To the left, because the box is sliding to the right. That's kinetic friction. What else is touching it? The string is touching it. And what can reach in from a distance? Gravity, Fg1, which is m1 times g. So let's take a look at this and see if this would get full points on an exam. It's a Freebody diagram. Is there only one normal force? Yes. So I can just call it N. I don't have to give it any subscript. Is there only one force of kinetic friction? Yes. So I'm good there. There's two friction forces and they are different. So I have to label them differently. I've got sub 1 and sub 2, right? Because they are different. You have to have different subscripts. Don't call them the same thing if they're different. And I've got two tensions, but I know they're equal. They're the same. So I can just call it T in both cases, right? So, so I'm okay with these free body diagrams. Now what we're going to do is say sum of the forces equals MA for each object. All right. So M1, M2. Now I've got sum of the forces on 1 is M1A, and sum of the forces on 2 is M2A. Now what I want to do is think about my directions a little bit. So let's do M1 first, and I'll pick a coordinate system for M1. It's kind of nice. There's no incline here, right? So everything is already vertical and horizontal. All the forces are already in either vertical or horizontal directions. So I'm good with that. I can leave them all like that. And what direction is this block accelerating? To the right in the horizontal direction. So I'll pick that as my positive direction as for my coordinate system. Where's my, I'm going to pick to the right and up as my directions. I'm not going to call them X and Y though. I'm going to call the horizontal parallel to the motion, parallel to the surface, and the other direction perpendicular. That's a perpendicular sign. So parallel and perpendicular. You'll see in a minute why I'm doing that. Okay, so let's do, this is going to be, we're going to break this up, right? Sum of the forces parallel is m times the acceleration in that direction, and the right is the positive direction, and sum of the forces perpendicular to the motion is m times 0, right? And we're saying up is the positive direction. So let's finish off our perpendicular direction first. So in the perpendicular direction, we're calling that's this one here, right? So we have one force that's in the positive direction and one force that's in the negative direction. So we'll take that into account in our equation here. The normal force minus m1g has to be 0. The normal force just equals the weight of the object. We knew that already because, why did we know that? Because the surface is horizontal and the string is horizontal, right? If the string was pulling at an angle, then that wouldn't be true. We'd have to figure it out from this equation. If the angle was an incline, if the surface was at an incline, that wouldn't be true, right? But in this case, it was simple, but not always simple. Okay, so now we know our normal force. Let's go back and look at our parallel direction. What's happening in the direction of motion? So that's this direction. And we have one force that's in the positive direction, that's tension, and one force that's in the negative direction, that's kinetic friction. I'm just going to call it A because it's the only acceleration we have, right? I guess we could call it A1. Should we call it A1? The acceleration of block 1. All right, now I know friction, is kinetic friction. I can plug a formula in for kinetic friction. As long as I know that block is moving, I know it's kinetic friction, and I can substitute in mu kinetic times the normal force. And I know what the normal force is, so I can substitute that in, and I get tension minus mu kinetic times m1g equals m1. These are m1s over here. m1, 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 a1. Okay? So now I have one equation, but two unknowns, tension and acceleration. So I need another equation. Luckily, there's another mass in my system. Every mass in my system is going to give me an equation from F equals ma. So I come over here to mass 2. And 2 doesn't have any forces perpendicular to the direction of motion. It only has forces parallel to the direction of motion. So I'm going to call this sum of the forces in the parallel direction has to equal M2 times A parallel. We okay with that? So now I have to pick a positive direction, right, for my mass 2. So here's my technique. The truth is, you can pick any direction you want to be positive. But if you pick up to be positive, the acceleration of 2 is not the same as the acceleration of 1. They are opposite directions. One is negative of the other one. So it's much simpler if your accelerations are all the same. So this is how I make sure my accelerations are always the same. Whatever for the first mass in my system, I kind of pick any direction I want. If I know the accelerations in some direction, I try to pick that as my positive direction, but it doesn't really matter. Pick any direction you want for your positive direction for the first one. And then that fixes the positive direction for everything else in your system. And if you do that, then your accelerations will all have the same sign. So when M1 goes to the right, I said that's my positive direction. When M1 goes to the right, what does M2 do? It goes down. So down has to be my positive direction for M2 if I want my accelerations to be the same. And I do. I want my accelerations to be the same. So I'm going to pick down, because really what's happening here is this is all one motion kind of. So I'm going to pick down as my positive direction. It's fixed by the positive direction of the other one. All right, so what do we get here? We've got, in our positive direction, we've got the force of gravity pulling down, M2G. In the negative direction, I've got a tension force. And that has to equal M2 times its acceleration, A2. Now let's compare I've got one equation with two unknowns and one equation with two unknowns over here. What's the relationship between the acceleration of block 1 and the acceleration of block 2? So with pulleys, it can get tricky. I'm sure there are some problems in the book where the accelerations are not the same, but here's the trick. Look and see what happens to the blocks, right? So if block 1 moves 1 meter, what happens to block 2 in my case? It also moves 1 meter, right? They are connected by a rope through a pulley. If block 1 moves 1 meter, block 2 moves 1 meter. So they are linked 1 to 1. If block 2 is moving at 2 meters per second, if block 1 is moving at 2 meters per second, block 2 is also moving at 2 meters per second. They are linked through that pulley 1 to 1. And if block 1 has some acceleration, whatever, 3 meters per second squared, block 2 has these same acceleration. They are linked 1 to 1. So that's the trick. If 1 moves 1 meter and 2 also moves 1 meter, then everything is linked together. The velocities have to be the same. The accelerations have to be the same. You can use pulleys. In fact, that's why we use pulleys in a lot of cases, is to gain some mechanical advantage. So we can put in a small force and lift something really heavy. That's oftentimes we do that. But when you put in a small force and lift something really heavy, you have to move that small force through a really big distance to get that heavy object to move through a small distance. So it's not 1 to 1 anymore. It's 2 to 1 or 4 to 1 but the ratio is always the same. So you can look and see if block 1 moves 1 meter and block 2 moves 0.5 meter, then the velocities will also be the same. If block 1 moves 1 meter per second, block 2 would be moving at 0.5 meter per second. And the accelerations would also have the same ratio. If block 1 had an acceleration of 1, the other block would have an acceleration of 0.5. Look at the distance. That's the easiest thing to spot. And the ratio is the same for velocity and for acceleration. In this case, in most of the cases we see it's 1 to 1. There are just a couple of cases you'll see in the book probably where it's 2 to 1 or some other deal. Okay. Let's see, there were some questions here. They are absolutely not moving with constant speed because, well, I guess we don't know that. But chances are there's acceleration. The force of gravity is acting on this block, and there's acceleration. I guess we'd have to be told what the mass of that block is and what the friction force is. There might be a case where they exactly cancel. The accelerations became the same because the pulley's massless. No, the pulley's mass does not matter. This pulley could have mass or not. The accelerations of these two blocks would still be the same because it's linked 1 to 1 ratio in terms of the movement and all the actions. Okay? Mass of the pulley only is for the tensions being the same on both sides. Okay. So we're ready to plug in some numbers now, right? So now we know, what did we just say? We just said that A1 equals A2. The magnitudes are the same. And because I was very careful with the directions, the signs are the same. So I'm just going to call them A. So I have tension minus mu M1G equals M1A. That's one equation with two unknowns. And I have M2G minus the tension is M2A. That's one equation with two unknowns. And so I can solve those, right? Two equations, two unknowns. I'm good. I can solve those now. Okay. So the reason I don't like X and Y over here, a lot of people would call this the X, Y directions. And I said I didn't like that. I liked parallel and perpendicular, right? Well, the reason I don't like X and Y is because what would you call it for M2? If you called it XY for M1 like this, how would you label the directions for 2? You'd probably stick with X being your horizontal and Y being your vertical, right? And so now you're thinking that these are two different motions. One is moving in the X direction, the other one's moving in the Y direction. And this is the way I would do it. I would say that my object is moving, my coordinate system is moving with M. If M1 is sliding this way, right? My vertical and horizontal directions, I'm calling them perpendicular and parallel. They move along the rope, and then they follow over the pulley. If this is the pulley, they follow over the pulley and down for block 2. So block 2, I've got my parallel to the direction of motion and perpendicular to the direction of motion. So my coordinate system, really what's happening here is this is happening, right? This is one direction. And my coordinate system just follows it along. And the way I would draw it is like this. This would be perpendicular. This would be parallel, right? My coordinate system would just follow the rope. And so that's why I called this parallel to the direction of motion. You see that? Parallel to the direction of motion. and I used down as my positive direction. I just followed the rope basically and said that's my positive. That's one. The pulley is changing the direction, but it's really a one-dimensional problem. The pulley makes it look kind of like a two-dimensional problem, but everything's moving in lines, right? And those lines are connected by that string. It's really a one-dimensional problem. Okay, let's think about this one. Question about my parallel. My parallel means in the direction of motion, parallel to the direction of motion. Perpendicular means perpendicular to the direction of motion. That's why I use those instead of X and Y. They're with respect to the motion. So parallel to the motion is left, right for the box that's moving left, right. It's up, down for the box that's moving up and down. Yeah, so if you like X and Y, that's fine, but just remember that those two directions are linked. When one box is moving horizontally, the other one moves vertically. Those are linked together. And don't think those are two different directions of motion, right? Those are linked together. So I kind of call them the same direction, but see what works for you. Okay, we've got a box sitting at rest on an incline. There's friction between the box and the incline. A rope is pulling on the box in a direction up and to the left, parallel to the incline. A physics student draws a Freebody diagram for the box. What, if anything, is wrong with the Freebody diagram? Can you see that okay? It didn't come out. This one says, I'll read the subscripts to you. They all say on the box. This one says on the box, on the box, on the box. Okay. But this one says on the incline. So this is the rope on the box. This is the incline on the box. This is the earth on the box. I'm just reading the print there that you can't read very well. And this is the box on the incline. Okay, that's the student's drawing. Okay, so let's hit the obvious one first. Then there's a lot to discuss. There we go. It says, are you allowed to combine Freebody diagrams? I thought Freebody diagrams were supposed to show forces that affect a single object. You are correct. So they have here, they've either mislabeled this force or they're not drawing their Freebody diagram correctly. Let's assume that they just mislabeled the subscripts on here. These should all be forces acting on the box if this is a Freebody diagram for the box. So let's just change this. This is wrong. And let's just change it to the incline on the box. Let's assume that the subscripts are wrong and that they really wanted the force going in that direction. Now, now there's a lot to talk about. Good. So a lot of talk about friction here. So are we okay with the normal force? We're good with that? And friction, sorry, tension in the rope, that looks good, right? And the weight, force of gravity toward the center of the earth, that looks good. So the only thing we're debating is the friction force. So let's think about what would happen if the rope was not there. If the rope was not there, the box would want to slide down the incline. If it wasn't sliding down the incline, if it was at rest, what direction would our static friction force be? It would be up the incline the way it's pictured here, right? We good with that? So we have a box sitting at rest on an incline. The static friction force is up the incline, right? Now we're going to pull with a little tiny force with the rope. Okay, little tiny force. So what just happened to our static friction force? It just got a little tiny bit smaller because the rope is holding up some of that, is providing some of the force that's preventing the box from sliding down. So the static friction force doesn't have to provide all of it. It can get a little bit smaller. Now we pull with a little bit more force with our rope. What happens to our static friction force? Gets a little bit smaller, right? Now we pull with a little bit more force and the static friction force gets a little bit smaller. Now we pull with a little bit more force and the friction force goes to 0. We're pulling with exact force with the rope that is preventing the object from sliding down the hill, and we don't need any friction force at all, 0 static friction force. Now we pull with a little bit more force. What does the box want to do now? It wants to go up the hill. I'm pulling with more force than what gravity is pulling down the incline with. So what does static friction do? Static friction has to go down. It's going to try to keep the box sitting where it is. It's going to point down the incline. And I pull a little harder and static friction force gets a little bit bigger in the downward direction, right? And I pull a little harder and it gets a little bigger in the downward direction. I keep pulling until the static friction force hits some maximum value in the down the hill direction. And then if I pull with any more than that, the box breaks free and starts to move up the incline. So that static friction force could point up the incline. It could be 0. It could point down the incline. We would need more information. Okay, yeah, think about that one. Make sure you understand that that static friction force reacts, and it depends on how much the rope, it's combining with the rope to keep that thing at rest. Okay. Let's do this one. got our baseball. I think we've seen this baseball before, right? Baseball being thrown from the left side of the, from the right, somebody over here threw the ball. So it's moving in this direction, right? It's moving in this direction, and it's going to end up over here at home plate. So it says a physics student watching the game produces this Freebody diagram for the baseball as it moves upward at point S along this path. And this is the explanation. I'm ignoring air resistance. W is the weight of the ball, and D is the force of the throw on the ball. What, if anything, is wrong with this Freebody diagram? Okay. The ball was thrown with a force, but where's the ball now? It's here. Where was it thrown from? Back here, right? Inertia, baby. There you go. So while it was in the person's hand, yeah, there was some force had to have been acting on it to get it to go in that direction. The instant it leaves contact with the hand, it's in free fall, right? The only force acting on it is the force of gravity. So no D. That's the correct free body diagram. Okay, good. Let's for this first one, let's draw a real free body diagram where we're drawing the shape of the object. So our object is the beam here. We've got this balance beam, this beam on this pivot point, and there's a box sitting on one side and there's a box sitting on the other side. So we're going to construct a free body diagram for the beam, but it's a massless beam. It says ignore the weight of the beam. So draw the beam, and then draw all the forces acting on the beam at the location where they're interacting with the beam. So we have object one sitting there, right? And so you could call that a number of things. You could say that there's a surface. Object one is interacting through a surface to the other object surface. So you could call that a normal force. We know what it is though, right? It's the weight of object one. but normal force 1 on the beam, we know that's going to be equal to m1g, right? And then we've got object 2 over here. I don't know, is it smaller? Yes, it is. We've got normal force 2 on the beam, and we know that has to equal m2g, right? And then there has to be, the beam's not going down, is it? So there has to be some upward force. That's that support point in the center. That's not in the center, it's off center. I'll call it F support. So we've got the support force, and we've got these two normal forces, or I guess if you wrote them as the weight, that would be okay. But really, it's an interaction with those objects. All right. Next one is a pendulum. Heavy ball swinging to the right at the end of a cable. Normal force going. Oh, you want to call this a normal force instead of a support force? That's fine. Normal, or you could call it a normal force. This is a Freebody diagram for the beam, right? So the boxes are pushing down on the beam. If you have a Freebody diagram for the boxes, then you have normal forces pushing up. Is that what you're saying? Okay, good. And it told us that, yeah, we're ignoring the weight of the beam. It says that ignore the weight of the beam. That was given. Okay. So this is how we're going to draw Freebody diagrams in a few weeks when we are dealing with objects that can rotate and things. All right, now we've got a ball swinging, heavy ball swinging at the end of a rope. Draw a Freebody diagram at this instant. Yeah, so if you just want to draw it the way it's done here, we've got a tension in the string, right, along the length of the string. And we have weight, force of gravity or weight that points toward the center of the earth. And you could leave it like that. What I would probably do if I was solving this problem is I would break up the weight. Why would I break up the weight? Into components. Because I'm thinking about what direction is the acceleration, right? What's this thing doing? It's really the coordinate system of interest is really this one. So I would break it up. I would make that my coordinate system. And how do I know? Because the acceleration is sort of in that coordinate system. That's how I think about the acceleration. And so so the tension is already in that coordinate system, and the force of gravity I would break up into its components that are tangent to the path and perpendicular to the path, or radial and tangential, I guess I should say. Okay, and then we've got this ball in midair, flying through the air. Ignore air resistance. Okay, we just did this one, right? I don't care how you want to call it, but it's the force of gravity is the only thing acting on it. If you call it mg or w or f sub g, either any of those are fine. Okay, we're good here. We're going to do stuff like this. We'll do something like this soon enough here. We're about to start circular motion here. Tomorrow, probably. Acceleration for this one. Yeah, there's acceleration. Because look at their Freebody diagram. There's only one force acting on it, right? So you can't have zero net force if there's only one force acting on something. There has to be at least one other one to cancel it out to have zero net force. So there's a net force here. There's acceleration in the downward direction. There's no acceleration horizontally. There are no horizontal forces. So we have no horizontal acceleration because we're ignoring air resistance, and we just have the force of gravity. Good. All right, so I want to do this one real quick. And I've posted these. We're going to do one right now. So I posted 3 of them. I posted this worksheet and 2 more on the Canvas site under modules. One of the modules says worksheets, handouts, worksheets, something like that. Look for the module that says worksheets or handouts. There's 3. They all say Freebody Diagram Worksheet 1, Freebody Diagram Worksheet 2, and Worksheet 3. So there's 3 of them there. One of them is this one, and the other 2 we're going to do tomorrow. So I want you to take a look at them first. I think these are really helpful for doing Freebody diagrams. So let's take a look at this first one here. So number one is right here. This number 1. It says construct a motion diagram for the block whose free body diagram is shown to the right. So here you're going to draw your motion diagram. Remember motion diagrams? Motion diagrams are those dots, like a strobe light going off. Where is the object here? Where is it next? Where is it next? And those dots are placed at equal time intervals, like a strobe light going off. Is it moving up or down? It's not moving up or down, right? How do we know that? Well, we look at the vectors here. We have a vector in this direction that's two units long, and we have one in this direction that's 1.5, and one here that's 1/2. So we have 2 units of force up, 2 units of force down. We have a net force of 0 in the vertical direction. So as long as it didn't start out moving vertically, it's not going to. So I'm assuming that means it's just being dragged across the floor. So now we look at the horizontal direction, right? there's 1.5 units of force to the left, but only 1 unit of force to the right, right? If we break up the tension into a horizontal component and a vertical component, we have 1 unit to the right, 1.5 to the left. So what direction is the acceleration? To the left. To the left. The net force is to the left. But there's tension in that string, right? So the only way we can have tension in that string is if we're pulling on the box a little bit. So the box must be moving to the right, but slowing down. Does that make sense? So if the box is moving to the right, I'll use red. So it's doing something like this, right? Moving to the right and slowing down. The net force is to the left, but the box is moving to the right. Yeah, I think that's the only way you can get a tension in a string to the right. I think that's the only way this would work. Okay, so my suggestion is continue, go to the Canvas site under modules, take a look at these 3. Number 2 here is next. Take a look at number 2. And then there's a 3rd one here on this sheet. See if you can, the questions are kind of hidden in here, right? They want you to fill in stuff and fill in the normal force. And so the questions are kind of hidden in there, but fill out those sheets best you can. I think they're very helpful for Freebody diagrams. We'll go over them tomorrow. So the box can't be moving at constant speed because there's a net force, right? If you're looking at this, the force, I'll use green here, the total force to the right is 1 unit long. The total force to the left is 1.5 units long. So there's a net force there. There's not 0 net force. So there has to be acceleration to the left. Okay, I'm going to stop recording. I'll stick around and see if there's some questions here I can answer, but I'll stop the recording now and we'll see you tomorrow.